looking at, again, the topic of related rates. And basically the idea in related rates is, you have objects that are moving. You have, police cars going towards a certain direction, chasing a car. You have a ladder that is falling down the side. You have a balloon that's being filled up with air. You have a cone that is being filled with sand, or they're dumping the sand out of a conical container. So things are changing. And things are changing as time goes by. So in this section, most of the derivatives will be taken with respect to the time variable. So for example, if I want to talk about how fast is the volume of this cone changing, how would I represent that as a derivative? How fast the volume of a cone changes? Well, if my volume is represented by V, I could write dV dt. This represents the rate of change of volume per unit change in time. If I'm talking about how fast is the distance changing, if I'm calling that distance x, then the distance, the rate of change of distance or velocity, I can write it as dx over dt. If I call that distance y, I can then write the rate of change of distance as dy over dt. Let's say that there was a ladder that was sliding, and this angle is theta. I want to know how fast is the angle theta changing. How would you write that as a derivative? How fast? D theta over dt. So as you can see, everything in this section is going to be differentiated with respect to the time variable, because things are changing with time. And why do they call this section related rates? Because usually they will give you one rate of change. Like they might say the ladder is sliding at a rate of 3 feet per second. And then they want another rate of change, such as the rate of change of the angle. Okay, so they give you one rate of change. They're asking you to find a related rate of change. So that's the bottom line for most of these questions. Okay, so let's go ahead and take a look at this first example. And the template shows you the steps that we need to take pretty much in every one of these questions. We always start with a graph. So in this case, we have an airplane that is going to fly over a radar tracking station, and it's flying at a constant altitude of 6 miles. Again, there are various ways that you could be doing this graph. Let's say that this is my radar station, and the airplane is coming from here, going that way. And it's a constant altitude. So this altitude here is 6 miles. Let's say this is my radar tracking station. Okay. The question is, if S is the distance between the plane and the tracking station, so if this distance is S, and that distance is decreasing at a rate of 400 miles per hour, what is the speed of the plane? So we have a very rough picture. This plane is going that way. This is the radar tracking station over here. It's flying at a constant altitude. And we're asked to find something. We're asked to find the speed of the plane. So, we've done the first step, which is to draw a very rough picture of the situation so we can visualize what is happening here. Second step is state the goal, because many times I think students, they don't even know what they're looking for, and they're doing circular arguments. So let's put it nice and clear at the top of our page. What is it that we're trying to find for these questions? Okay, so if we want to find the speed of the plane, let's say that I call this distance x. So the speed of the plane will be the rate at which that distance is being traveled. So it's a derivative. What is that distance then? dx over dt. So the goal is to find dx over dt, the rate at which that distance x is being traveled by the plane. How fast is it being traveled? That's going to be the velocity of the plane. Okay, then they want us to write down what is given. Write down the given related rates. So for example, they said that the distance s, which is the distance between plane and the tracking station, is decreasing at a rate of 400 miles per hour. How could I write that down as a derivative? The rate of change of distance s is decreasing at 400 miles per hour. So what should I write? ds dt. Good. Somebody even thought about the negative one. It is negative because that distance is decreasing, right? So we're going to put negative 400, and the units are miles per hour. But that distance may be a variable. That rate may be a variable rate. It may not be the same rate at any given moment. We know this at the moment when at the moment when s equals to 10. Because if you think about it, when the plane is very far away, that distance is closing slowly, right? But as the plane is really, really close to the tracking station, this distance is going to be changing really, really fast, right? Right there. So it's not really a constant rate, the rate of change of ds over dt, okay? Okay, so we did the first 3 steps. We did the picture, the goal, and we wrote down the given related rates. What we need right now is, remember, since we're trying to find dx over dt, and we are given ds over dt, we need to write an equation that somehow we can get x and s out of it. We can get dx dt and ds dt out of it. What equation do you think could relate the variables in question and also maybe something that we know? For example, we know one side is 6, right? You can use that in your equation. What equation do you think we could use here? Good, you have a right triangle, right? At any given moment, you have a right triangle as this plane is moving, right? With the sides of 6, x, and s. And the Pythagorean theorem, you will see, it will get a lot of use in this chapter, in this section. So what would the Pythagorean theorem say about this right triangle? 6 squared plus x squared equals to s squared. Now, do I need a variable for the 6? I put a 6. Should I have put like a y there, do you think? Or can I keep it as a 6? I can keep that as a 6 because as time goes by, that side is not changing, right? So that is truly a constant with respect to time. But it doesn't change as time goes by. So that's going to stay as a constant. Let me just rewrite this. So we have 36 plus x squared equals to s squared. Okay, now the next step. So see, we're trying to find dx dt, and we know ds dt. How are you going to get dx dt and ds dt out of an equation like this? Any guesses? We're going to need to differentiate both sides with respect to the time variable. And you will find that in every one of these questions in this section, once you write your equation, you will always be differentiating with respect to time. Why? Because things are changing with time. You're trying to find the rate of change with respect to time. So that's always going to be the case. Find an equation that applies in that case, and then differentiate it with respect to time on both sides. So let's do that. Derivative of 36 with respect to t would be what? 0. Derivative of x squared with respect to t would be. Now let's think about it. We're not differentiating it with respect to x, but we're differentiating it with respect to time. So x is like a function of time. It's changing as time goes by, right? So 2x times dx dt, right? The derivative of the inside with respect to the time variable, so dx dt. So as you can see, we're using like the chain rule there. We're also using like the implicit differentiation there, right? You multiply everything with the derivative of the inside, which is dx over dt, equals, how about on the right-hand side? What is the derivative of s squared with respect to the time variable? 2s. Is s also changing with time? Yeah, so s is really a function of time, right? It's really s of t in a sense. So 2s times ds over dt. Now, in implicit differentiation, only y got the special treatment, right? Here, basically, every variable is going to get that special treatment because every variable is a function of time, and we're differentiating everything with respect to time. Now, if you had that equation, x squared equals s squared, if you were differentiating it with respect to x, what would be the derivative of the left-hand side? 2x, right? dx would be 1, right? But you're differentiating with respect to time. That's why we're multiplying it by the derivative inside dx dt, and we keep it there. Okay. Now, what else do we know? Do we know what x is, or do we know what s is? Okay, we know what s is. They said at the moment when s equals 10. Okay, sorry, I put this in the wrong place, it seems, but it doesn't really matter. We need the equation. Is it going to let me move that? Well, assume that this is in the next step, in step number 5. For cone problems, we'll have an extra thing in that bracket space. So we differentiated already. So we've done step 5 already. Okay, now step 6 says plug in all the constants from step 3 into the equation you got here, right above here. Okay, so the constants, 2x dx dt. Do we know what x is right now? We know what S is, right? S is 10. So I'm going to put, so if S is 10, so I'm just going to put this over here, but you guys get the idea. So I have 2S ds dt. S was 10. Do I know what ds over dt is? Yeah, that was given, right? Negative 400. Okay, how about this part? 2x dx over dt. Let me leave at the moment the space for x empty. We're going to fill it in. And dx over dt is exactly what we're trying to find out, right? That was the goal. If you look at step number 2, that was the goal, dx over dt. So if I can just determine x and put it in here, I have basically solved the problem. I'll then just solve for dx over dt and we're done. Okay, how do we get x? So if you know what s is, this side was 6, this side was 10, right? So we just need to know what is this side, what is x at that moment. Some of you will already guess this. There's a famous triangle, 6, 8, 10. Right, like the 3, 4, 5 triangle is famous also. But if you don't remember it, let's just solve the Pythagorean equation here. So that side is called x. So what we have here is like 6 squared plus x squared equals to 10 squared. So x squared equals to 100 minus 36. X squared is 64. So x is 8. So since I know what x is, I can plug in this space right now. X, we just determined that to be 8. And go ahead and find out what dx over dt is by dividing both sides by 16. So on the right-hand side, I have 2 times 10, or 20 times negative 400 divided by 16. Of course, you could simplify it a little bit, etc. Or you can just put it all in the calculator and get a result. So there I'm getting 500. And what will the units be for this? Dx over dt. That should be units for x divided by units for t. So what were the units for x here? For distance, what units did we use so far? Miles, and for time we use hours. So the resulting expression will also be miles per hour. And I shouldn't forget my negative as well. The negative indicates that that distance is shrinking, or that the object is going in the opposite direction. So again, if a quantity is getting lesser and lesser as time goes by, its derivative is going to be negative. Questions? Yes?
What is S again?
S, let's look at our picture. Let's look at the picture. That was the direct distance between the plane and the radar tracking station. That was the direct distance from the plane to the radar. 6 miles was the vertical height. That was the plane was flying at a constant altitude of 6 miles. But S is the direct distance between the plane and the radar tracking station. So as this plane gets closer to be right on the top of the radar tracking station, what's happening to S? Can you see that it's actually decreasing based on the picture, right? So again, it makes sense that the answer turned out to be negative.
So S is technically an
No,
angle.
no, no, no. S is not an angle. As you can see in the picture, S is this distance from here to here. Okay? So S is the direct distance between the radar tracking station and the plane. Okay. Yes, another question, Joey? Mm-hmm.
It was 500.
Oh, no, no, it was negative 500. Yes, yes, yes. Mm-hmm. Again, the negative indicating that distance x is getting smaller and smaller as time goes by. Okay, so let's do another example on related rates. Okay. Let's do example number 5 on the next page. I picked that one first because it's going to be more similar to this example than any other example I have on that sheet. So let's do example 5, which is a very similar question to the one that we just solved. Okay, example number 5. first thing I ask you is, can you do a picture for the given situation? Create a picture. Are there any extra sheets that were passed back? Any extra sheets? Thank you very much. Also over there. Thank you. Okay, I'll get those later. Thanks. So let's say, again, there are many ways to possibly create a picture for the situation, but let's say one plane is going like this, and the other plane is going this way. So we have one plane over here, another plane over there. So they're going towards each other at right angles. Right, but just imagine they're on the same altitude, but they're still going towards the same point. So look as if you're looking from the top. Okay. Yeah, they're still going at each other at 90-degree angle. So basically, this is like a recipe for disaster. It looks like they're going to collapse after a point if they continue on the same track. So they have to switch tracks after a certain point, right? So I'm going to call it, they didn't give us enough information, but I can just call this one my plane A, and this one my plane B. You know, you could have done the opposite. It doesn't really matter, but just be consistent from that point forward. And this is the distance between the two planes. And I usually call the horizontal distances x and the vertical distances y. In this case, really, they're all at the same altitude, but I'm just going to call that distance x and y. You could have named it any two variables that you like. It doesn't really have to be x and y. And the third distance between them, that's also changing. I'll call that one z, let's say. Again, you could call them A, B, and C, for example. It would work just fine. And I'm going to make a note of a few things that are given here. So plane A is moving at a rate of 300 miles per hour. So moving at 300 miles per hour. And plane B is moving at a rate of 450 miles per hour. And they want to know the rate, the distance between them is closing at a certain moment in time. Okay. First of all, let's write down, if you're following the template, just like we done the last question, first we want to write down, what is the goal here? They said, at what rate is the distance between them closing? So how can you write that as a derivative? That's our goal. At what rate is the direct distance between them closing? How would you write that as a derivative? How would you define the distance between the two planes? Here's one plane. Here's the other plane. The distance between them is defined by z. So now we're talking about the rate at which that is changing. At what rate is the distance between them closing? dz dt. We want to find dz dt, the rate at which the distance between the planes changing. Any questions about this, first of all, about the goal? We're trying to find dz dt, the rate of change of the distance between them. Okay. In number 3 in our template, we're asked to write down the given related rates as derivatives. Given that, what do we know about dx over dt here? And again, that distance is shrinking, so keep that in mind as they are converging towards this point. And this is right angles. So what do we know about dx dt? It's 450, but positive or negative? It should be negative. dx dt should be negative 450 miles per hour. Yes, because this plane is going that way, and what is happening to the distance x? It's getting smaller, right? Therefore, the x dt is a derivative. The rate of change is negative 450 miles per hour. Okay. Then they also said that plane B is moving at a rate of 450. Okay, we already did that one. Plane A is moving at a rate of 300 miles per hour. So how would you write that one? dy dt equals 300 or negative. Because this distance is shrinking as well, right? The plane is going north or in that direction towards the point, right? So that's also negative 300, negative. Pardon me? The reason it's negative is because the distance y is getting smaller and smaller. What is the distance y? Y is the distance from where it is right now to that point that it's going towards. So as it travels in that direction, that distance is getting smaller. Therefore, we have a negative rate of change. Okay. Okay. And we don't know the answer for dz dt right now. That's our goal. But give me your estimate. Do you think it's going to be positive or negative when we're all done with this problem? Negative, because dz dt is also shrinking, right? The rate of change of z is also getting smaller, so that will also be negative. And if we don't get a negative, we should be suspicious of our work. Okay. Then the question says, write an equation that relates all the variables. This is very similar to the last problem, except we don't have a constant side. All three sides are changing, right? So an equation that relates all the variables would be exactly. That would be x squared plus y squared equals z squared. Again, the reason I could write that is because they're flying towards the same point at right angles, and at any given moment, that triangular relationship is holding true no matter where you look at it, like whether they're at that point in time or whether they're here, they've moved further, or whether they're here. You always have a right triangle, so you can use that during any point in this journey. You can use that right triangle. Okay, what will I do next? No, we don't want to plug anything yet. Look at your, after step number 4, step number 5 says, differentiate both sides with respect to which variable? T. Always you differentiate with respect to time because things are changing with time. One of the biggest dangers is to plug the constants in too early. If you plug them too early, there's nothing left to differentiate. And how are you going to get dx dt, dz dt out of that? So you want to remember, first you differentiate and then you substitute the values. So first of all, what I'm doing next is differentiate both sides with respect to the t variable. And here is what we get. Who can tell me? 2x times dx dt, right? Plus 2y times dy dt equals 2z times dz dt. I can right away divide both sides of this equation by 2, so I can get rid of the 2's right away. Now let's plug in what we know. Okay, x is the distance that plane B is away from that intersection. And what is that distance? They said plane B is 400 miles away, right? That's my distance, x. That's 400. And what do I know about dx dt? Right, we got that earlier. That was negative 450. Plus y. That's the distance that A is away from the intersection. And A was 250 miles from the intersection. Times dy dt. And what do we know about that? Negative 300. On the right-hand side, we don't know what z is right now. I'm going to put just the empty parentheses there. And dz over dt, that's exactly what we're trying to find out, right? So that's a healthy variable to have in your equation. You want to keep it in there because we want to solve for that variable, okay? So the only thing I need to know right now is z. And how in the world are we going to get z? Once again, the good old Pythagorean theorem comes to the rescue, as it will many times in this chapter. It's interesting because I was just recently looking at a book. There's a book called Journey Through the Genius, and they look at the contributions that a lot of mathematicians made, and they were talking about Euclid's Elements. That was one of the first times the proof was published, and it's a very intricate proof. You would be amazed. People in, like almost 500 BC, they were able to come up with this proof, and they proved the Pythagorean theorem. And today, I think there's a book out there about the Pythagorean theorem. Apparently, it has like hundreds of proofs of the Pythagorean theorem. But every one of them very, very interesting and very involved. But it's been around a very long time, as you can see, almost more than 2,000 years, as you can see. All right, so here we have one side we called y, and that side was, is it at the moment, when plane A is 250 away, 250 miles, and plane B was 400 miles away. At that moment, we're trying to find out this distance z. So let's do that over here. Z squared equals 250 squared plus 400 squared. And z equals, let's go ahead and take the square root of the right-hand side to see what z is. And what do we get? Let's say to the nearest tenths. Or if you prefer, you could leave everything under the square root. Only in the last step you could round your answers. Either way is okay. I'm going to write the answer as 471.7 miles. Okay. So now let's finish the question. To solve for dz dt, we're just going to divide both sides by that number in front of dz dt, right? So I'm going to go ahead and get the single number for the left-hand side. Ryan, what did you get? Negative 60,000. 360,000 divided by 471.7. And did you do the ratio as well? And what did you get for that? Oh, I want to know a single number for the top. That's what I was looking for. I thought that's what you gave me. So what is the single number that is on the top? Negative 255,000. Okay. And divide that by 471.7. And what do we get as a single number? Negative 540.6. And the units would be miles per hour. And are we surprised that we got a negative result here for the rate of change of that distance z? No, we can clearly see that distance z is shrinking as time goes by. So it makes sense that dz dt turned out to be negative in that instance as well. Any questions about the solution before we take a look at another example? Okay. Yes, Ryan? Yes, because basically you could factor out a 2 from both sides. Like from this side, if you factor out a 2, and then you can divide both sides by 2, they'll cancel. Yes. Okay. Let's do another example. Let's see which one to do from the handout. Let's go to this one. The one about the ladder that is leaning on a wall. Let's find that example from the notes. I think it's example number 3. Right. Okay, I want to give you a few moments to do a picture, find an equation that relates all the variables, and then we'll go ahead and solve it together after that. already have a picture here, so I'm going to go ahead and copy my picture, so I have to draw it again. If it works, copy. There we go. Okay, it worked. Okay. So for this question, we don't have to be concerned about that angle theta. Okay, so there we have a picture. As you can see, I labeled the length of the ladder as 20. I didn't have to call that side z because I know that as time goes by, z is not changing for this question. That length is always going to stay constant, so I put the constant right away. No need to introduce an extra variable. So they said, how fast is the top of the ladder moving when the base of the ladder is 8 feet from the wall? How fast is the top of the ladder moving? So as a derivative, what are they asking us here? dy dt. Find dy dt. How fast is that distance y changing as time goes by? Okay. And what's given to us? The rate at which it's pulled away from the wall, that's dx over dt. And is that positive or negative 1? Positive, because x is getting larger as this ladder moves that way. It's moving at a rate of 1 foot per second. And they want to know what dy over dt is at the moment when the ladder is 8 feet from the wall. So what is that, x or y? X. So they want to know this when x is equal to 8. Okay. What equation did you use? Once again, at any given moment, you have a right triangle. Believe me, we'll get to examples that doesn't use Pythagorean theorem, but this one still uses it because you have a right triangle, right? Yeah, a lot of, maybe 50% of the questions may be using it in this section, yes. So we have, once again, y squared. An equation that relates all the variables is y squared plus x squared equals to 20 squared, or 400. Now I'm going to differentiate both sides with respect to which variable? Always t, right? Things are changing as time goes by. So it's going to be 2y times dy dt, right? Plus 2x times dx dt equals to what? What is the derivative of a constant of 400? 0. The rate of change of the ladder is 0. It doesn't change at all, so this should be 0. Okay. Now, we can divide both sides of this equation by 2, so we can get rid of these unnecessary constants here, making our equation a little bit easier. Now, I need to have y times dy dt. Well, they give us x, so at the moment, I don't know what y is, but can I figure it out? Yes, if x is 8, y is unknown, and this side is a fixed number of 20, we can get what y is once again using the same equation over again. Y squared plus 8 squared equals 20 squared. So y squared equals 400 minus 64. So y will be, I believe, the square root of 336. You can either get a number for it, or you can keep it like that, only round in the last step of your approximation. You can also do it that way. Either way is okay. So now that we know what y is, we can plug it in. Y is root 336. How about dy dt? Do we know what that is? That's what we're trying to find, so it's okay to keep it as such. Just keep it as dy dt in your equation. Plus, x is given as 8, and dx dt was 1. So the only unknown now is dy dt, and we can solve for it, right? I will subtract 8 from both sides and divide by root 336. Anybody who got a decimal answer for us? And it should be negative, right? Negative 0.4 or 0.44, either one would be okay as far as I'm concerned. So, and the units would be feet per seconds. Does it make sense that this turned out to be a negative quantity, dy dt? Because if that ladder is being pulled away on the bottom, the top is getting shrinking, right? The top distance is getting closer and closer to the ground, so dy dt is negative, and that makes sense in this situation. Now, I'm going to add a part B to this problem, part B. So would you please just add this following question? So we have the same picture, but this time I'm putting an angle of theta. The theta is the angle between the ladder and the horizontal. The question asks, find the rate of change of the angle theta at the same moment, at the moment when x is 8. Find the rate of change of the angle. Finally, we'll step away from the Pythagorean theorem here. So once again, we need the goal, we need to state what's given, and then we need to find an equation that relates all those variables. Let's begin with the goal. As a derivative, what are they asking here? Good, d theta dt, the rate of change of the angle theta as time goes by, that's precisely d theta dt. That's what they want to know. Find d theta dt when x is equal to 8, at the moment when x is 5, the base of the ladder is 8 feet from the wall. Okay, the given information is the same as given in the top of the problem, and that was the base of the ladder was moving at a rate of, that part of the problem hasn't changed, and what was that rate? Positive 1 foot per second, because this ladder was being pulled away in that direction, right, at a rate of 1 foot per second. That hasn't changed? Okay. But the equation has changed, because somehow you need to relate theta and x. You need to have theta and x in the same equation. What kind of an equation would that require? Definitely not the Pythagorean. There's not going to be an angle theta in there, right? So what equation could we use? We need a trig function here. To get a theta in there, we're going to need a trig function. Then the question becomes, which trig function would be the best one to use? We want to relate the side x, and you definitely want to make use of the hypotenuse of this triangle, because it's a fixed length. You want to use that in your equation. So cosine would be a really good choice here, because cosine would relate the adjacent side with the hypotenuse. That will work very well. Now, since we also did part A of this question, we also know what dy over dt is, right? In that regard, you could also use sine function, because you can then revert to your dy dt. But let's just keep it simple. Let's just use the cosine function as you suggested. So here's our equation we're going to use. Cosine theta equals, what is it equal to? In terms of variables first, x over 20. Right, adjacent over hypotenuse, that's x over 20. Okay, now we want to differentiate with respect to the variable t. And what do we get? Differentiate with respect to t. Okay, derivative of cosine theta with respect to t. Let's think about it. Remember, theta changes with time, right? Theta is a function of time. So what is the derivative of cosine of theta with respect to t? Good start. Negative sine theta times d theta dt. Okay. The right-hand side, I can really write it like this, 1 over 20 times x. I don't need the quotient rule there. It's a constant times a function. The constant remains. I just need to know what is the derivative of x with respect to time. Derivative of x with respect to t. That would be just 1 times dx dt, right? Or just dx dt. Okay, any questions about my derivative here? Any questions? Yes. At the end. When we're determining like sine theta, we're going to use that right now. Again, it's very important to remember. First, you differentiate, then you substitute your constants in. Okay, if you plug them in too early, you're going to lose your equation. You won't have anything to differentiate, basically. Okay, so now we need to find dx over dt, of course, is given. That's no problem. So this is 1 over 20. Dx over dt was 1. I might as well put it in there. D theta dt, again, that's a good variable to have in your equation because we're looking for that, right? We're trying to find d theta dt. The only thing that we need to know right now is sine of theta. And let me not forget the negative. I'll put it here. I need to know what sine of theta is in this triangle. Let me draw it down here. I need to know sine of theta. So this side is 8. This side is 20. And didn't we already know what y was also from the previous work that we did? What was this? Root 336, right? So we already got that in the last step, root 336. So I need to know right now sine of this angle theta. So what should I have? Exactly, opposite over hypotenuse, which is root 336 divided by 20. Opposite over hypotenuse for the sine. And finally, to solve for d theta dt, you know, when you're dividing by this fraction, both sides, it's basically going to appear on the other side as the reciprocal fraction, right? So it's going to appear as negative 20 over root 336 times, we already have 1 over 20 there, and the 20s cancel exactly. So let's see now, what is negative 1 over root 336? That is going to be the rate of change of that angle per unit of time. Time was in seconds here. And anytime you're using calculus to get an angle, you have made certain assumptions, like the area of sine is cosine only when theta is in radians. Okay, if it's not in radians, there's an extra factor there of like pi or 180 or something like that. So anytime you use calculus to get to a point, your answer will always automatically appear in radians per second. In this case, theta will automatically be in radians when you get it back here. So is it decimal? Did you get 0.0 something? 0.055. And the units would be units for theta over units for time. That's going to be radians per second. And it makes sense this turned out to be negative because as the ladder is sliding down, it's basically getting more and more flat. That angle is becoming smaller and smaller, so the answer did turn out to be negative there. Okay, let's go back to the top of the problem. Any questions about how we found d theta dt in this equation? Go back up. Okay, go back to the bottom. Sure. So when the question asks find d theta dt, make sure that you're using a trigonometric function and you're going to differentiate that with respect to time. Amy had a question. Yes, please. How come it's 1 over 20? Dx dt was 1, correct? So are we looking at the right-hand side over here? Are you looking like over here? Right, because of the given question. Find the rate of change of the angle when x equals 8. The one was dx dt. That was given in the previous part of the question. Remember, they were pulling this ladder away at a rate of 1 foot per second. So that part is still the same for this question. That's dx dt. That was given as 1, and that's what we used over here. We plugged in 1 for dx dt. Okay? And we plugged in 8 for x down here. That helped us to get our sine of that angle, sine of theta. So we still use the 8, but down here. Okay? Any other questions? Yes?
The 8 doesn't come with the equation at all.
No, it was only helpful in determining the sine theta, basically. Yes. Yes, Joey? Okay, the negative was first introduced when we differentiated cosine, right? There, cosine is negative sine. And we had to keep that negative in our equation because we got it through differentiation. Yes, exactly. So it was brought in from the differentiation process. Okay, we're going to do now example number 2. A very typical question known as a cone problem. You will see a lot of cone problems in this section. So water is flowing at a rate of 50 cubic meters per minute from a shallow, my picture is not really up to scale here, but it's very wide and not as tall. According to the dimensions, it's 45 feet for the radius, in this case meters for the radius, and only 5 meters deep. And water is basically flowing out of this container at a rate of 50 cubic meters per minute. In part A, we're going to find how fast the water level is falling at the moment when the water is 5 meters deep. How fast is the water level falling? Okay, I'm going to represent the water level in here in blue. So the water level could be at any point in this cone. It doesn't have to go all the way to the rim because it's flowing out of the container. It's getting lesser and lesser. So it could be at any level there. We don't know where it is right now. But we do know the outside dimensions. The outside dimensions are the base radius is 45 meters. And the base and the height for the entire cone is 6 meters. As you can see, definitely not up to scale here. And further, I will call the depth of the water in this container, I'm going to call that H. And whatever the radius is at that moment for the actual water in the container, I'm going to call that R. The radius of the water in the container, I'm going to call that R. So the outside dimensions are 45 meters for the radius, 6 meters for the height. And for the water that is actually in the container, I'm calling the radius R and the height H. That's changing. As this water flows out of this container, R and H are changing, right? That's why I assign variable names for those. Whereas the outside dimensions are not changing. That's why I'm putting actual constant for those, 45 for the radius and H for the height. Okay, let's try to write down the first 3 things, which are really the most important steps in my opinion. The goal, what's given, and the equation that will relate the variables. The goal, what's given to us, and the equation that will relate the variables with each other. Okay. So let's do part A first. What is the goal in part A? What are we trying to find? Good. I heard from a lot of students said the same thing. I'm happy to hear that. So dH dt. How fast is the water level falling? That's clearly going to be dH dt. At the moment when water is 5 meters deep, so that's at the moment when H equals 5. I want to find that. Okay, what's given? What is that 50 cubic meters per minute? What is that, 50 cubic meters per minute? You know what? The units are very important in telling you what this says. Cubic meters is the unit for what usually? Volume, exactly. So this is the change of volume then. How would you write it as a derivative? dV dt. But is it going to be positive or negative? Every time you write a derivative, think about it before you finish writing it down. In this case, water is flowing out from this container. The volume is decreasing as time goes by. So we should put plus or minus? Negative, exactly, minus. If you will see other questions where they're filling in a container with sand or some materials, in that case it would be an example with a positive. dV/dt. In this case, cubic meters per minute. Again, units are very important in telling us what's exactly given to us. In this case, cubic meters automatically reminds us this should be volume. Okay, an equation that can relate the volume of a cone with the height of a cone. What equation could we use there? How about the volume equation for a cone? Luckily, you don't have to memorize the volume equation for a cone. I will give this to you for a cone or sphere. You don't have to memorize. I'll give it to you for a cone. Here's the equation. Volume equals 1/3 pi r square h. Basically, what this equation is telling me is if you took like a cylinder of, the volume of a cylinder will be pi r square h, right? This is saying like you can squeeze in three cones, maybe put one like this and two upside down that way. You can basically, it's telling you that the volume for a cone is 1/3 that of a cylinder with the same radius, okay? But you don't have to memorize, okay? We do have a slight problem here, and this is when we're going to refer to the clause in your template. Remember the template I gave you earlier? It said for cone problems only in step number 4. What did it say? For cone problems only. Use similar triangle ratios to write the equation in one variable only. Because right now we have an r squared and an h on the right-hand side. And if we were to differentiate that equation, we're going to have to use the product rule. It's going to be messy, and even then we may have to do further fancy things. So to avoid messiness, we're going to try to get rid of one of the variables there, okay? Again, because it's in the product form, we don't want to worry about the product rule and further problems that could come with that. So here's how we're going to get rid of one of the variables. Take a look back to this picture that we have up here, and I'm going to just redraw it like a skeleton of that, okay? This is the outside dimensions, just a cross-section of it. This side was 6, this side was 45. Again, please excuse the bad scaling there. Looks like 6 is bigger than 45, but it just gives you the general idea. And inside you have water. Let me use that. So for the water, this is the radius, and this is the height, whereas the 6 refers to the outside dimensions of the container for the height. Okay, what can we use here to write r in terms of h? What is the relationship between r and h? Any thoughts? We have to use a little bit of geometry here. Similar triangles. Does anybody remember that idea? So there are several ways to do it. You could say r over 45 equals h over 6. Or you could say the ratio of r over h in the small triangle equals to the same corresponding size in the big triangle, which would be 45 over 6. Either way you go, you're going to be able to continue the problem just fine. So you can use either ratio that you prefer. Okay. Now, we want to find the h dt, right? So I want to keep the h in this equation. I need to get rid of the r. I need to know what r is in terms of h. I want to keep the h in there so I can find the h dt in the end, okay? So let's write what r is then. R is 45 over 6 times h, multiplying both sides by h. R is 45 over 6 times h. Can you just simplify that for me, that fraction? Divide the top by 3 and the bottom by 3, right? So 15 over 2h, or 7.58, right? So now we know r in terms of h. We can come back to our equation and plug it in. So volume equals 1/3 times pi times r squared. Now you got to be careful here. The entire r has to be squared. 15 over 2h squared. And what else should I have? One thing I'm missing in my equation is what? The last h in there. Let's not forget about that one, right? Okay, now I'm going to distribute that squaring. Just basically square each and every number under that parentheses. So we have 1/3 pi. Okay, if you square the 15, you get 225. If you square the 2, you get 4. If you square the h, you get h squared. But don't forget the h on the outside. And I want to clean it all up a little bit. Let's rewrite our volume equation. Does 3 go into 225? If so, let's simplify it. How can I know? I added the digits of 2, 2, and 5. That's 9. If it's divisible by 3, then the number will be divisible by 3. So going on to 225 over 3. What do you get? 75. So now we have 75 pi over 4 times what? H cubed. So far, have we done any differentiation? No, all we have done is simplify the volume equation as much as possible. Yes, questions?
4 there, why did it stay the same? Well, we were going to move the 225 over the 3. We had that 225 over 12, multiply those two fractions together.
Right, and then simplify. You can also do it that way. You can do
5 over 12 goes into 225?
No, 3 goes into 225 and 3 goes into 12. You can simplify your fraction, okay? Okay, so now that we have our volume equation, we're ready to differentiate it, okay? And we're going to differentiate it with respect to which variable? Always with respect to t, right? Differentiate with respect to t because things are changing with time, so we always differentiate with respect to t in this section. So on the left-hand side, it's going to be derivative of volume with respect to t, that's just dv dt. Okay? On the right-hand side, you have a number times h cubed. Okay? That number remains. What is the derivative of h cubed with respect to t? 3h squared dh dt. Okay, basically think of this as like 3x squared. How do you differentiate 3x squared? The 3 stays there, right, and you differentiate the 2x, and you multiply with that. So it's the same idea. You have a constant times a function. The constant remains, and you're just multiplying it with the derivative of that function next to the number. Okay. Okay, now do we know what h is at the given moment in time? They said at the moment when h was 5. I'll go right back to it, but I just want to double check. So we are given h, and we're trying to find dh dt. So we are given h, and h is 5. So let's go ahead and plug h equals 5 into this equation. And what else do we know? Do we know dv dt? What was that? Negative 50, right? So let's also put that in there. Negative 50 equals 75 pi. Actually, I might as well multiply 3 times 75. And looks like that's going to be 225 pi over 4. For h squared, I'm going to put in, for h, I'll put in 5, so that'll be 25 in there. And then we have dh dt at the end. Okay, how do we solve this equation for dh dt? What should I do first? You could do this in one shot, but if you want to do it in 2 steps, first multiply both sides by 4, and then divide by the coefficient. That would be the easiest way, I think. So first multiply both sides by 4. So on this side, the 4's cancel. And then in the next step, divide by the coefficient. So dh dt equals negative 200 divided by, so I have 225 pi times 25. Now, if you're going to do it on the calculator, you're going to need another set of parentheses for the denominator. So make sure you do it as such. Now let's see what we're getting. Good, negative 0.011. And how about the units? We found dh dt. The volume was given in terms of cubic, what was it, cubic meters per minute. So this will be then what? Meters per minute. The unit for length will be just meters, and the time is still minutes, so meters per minute. Yes, question? The given was 50 cubic meters, and that represented the rate of change of the volume. That was the given information, right?
Yeah, that was cubic meters. I mean, why is this?
Because the answer we got is for age.
Oh, you're just looking for age?
Right, right. And h represents distance, so units will be the units for the distance. Okay. Okay, and part B actually is going to be very easy once we have part A in hand, so we know what dh over dt is. Part A was asking, rather B is asking, how fast is the radius changing? How fast is the radius changing? How would you write that as a derivative? How fast is the radius changing? Do you want to know what the RDT is this time? You might say, wait a minute, do I have to go back and do everything again? No, you don't have to do everything again. There's a very simple way to get the R over dt. Since we know what the h over dt is, give me an equation that relates R and H together. An equation that relates R and H. We had that already up there, didn't we? What was it? Right here we had R equals 15 over 2H, correct? R equals 15 over 2H. From our similar triangles, we want to know the RDT right now, so what should we do? We know the HDT, we want to find the RDT, so what should I be doing to this equation? Good, take the derivative with respect to t of both sides. On the left-hand side, you will have the R over dt. On the right-hand side, a constant times a function, the constant remains, and it's going to be derivative of h with respect to time, the HDT. We already know the HDT, right? Right there. So then tell me what you get for the RDT then. Right. And what about the units? Units for R divided by units for T. Units for R is the distance units, right? Like meters. And time was in minutes. And does it make sense these came out negative? Yes, because the water is leaking out of this container, the radius is going to shrink, and the height is going to shrink. It makes sense that they all came out to be negative.